As we continue our discussion about tests for convergence or divergence of infinite series, we run into this one called the root test, which is it's stated in a similar way that the ratio test is stated. Here's the root test. We have some series, sum of a sub n's, and of course we're assuming this is infinite, so n equal 1 to infinity or some such thing. Three situations. One, the series converges absolutely if the limit of the nth root of the absolute value of the terms is less than 1. The nth root of the absolute value of the a sub n's is less than 1. The limit of that of those expressions is less than 1. So we know when it converges, and converges absolutely. We'll address that again in a moment. The series diverges if that limit of this nth root of the absolute value of the terms is greater than 1 or infinite. Obviously, it'd be greater than 1 if it was infinite. So if it's greater than 1, if that limit is in fact equal to 1, then the root test is inconclusive. We don't know whether it converges or diverges. It could do either one. So we'd have to use a different test altogether. Now let's remember that this converges absolutely means that the series converges, and furthermore, the series of the term absolute value of the terms also converges. Converges absolutely is stronger than just converges, because you can have some of your terms being negative, and if you're adding up positive and negatives, certainly that's going to be smaller than adding up just positives. So you're adding up just positives, that'd be absolute values. So you could have something where you're adding up positive and negatives and it converge, but adding up all positives, it would diverge. And that's the idea. Saying converges absolutely is a stronger meaning than just converges, period. Now also notice here, like the ratio test, this test does not require any other series to compare to. It uses only the terms of itself. So it's easy to apply because the conditions are very slight. I like this test a lot and the ratio test a lot. And here's a note that this is clearly this test is a good test for series that involve nth powers, because we're taking nth roots. So it's a really good time to consider using the root test. Well, let's look at an example. Now, this is just emphasizing again that the root test is good for series involving nth powers. And so this very first example, we're supposed to determine the convergence or divergence of the series, which is the sum of from n equal 1 to infinity of n over 3 to the n power. Now, this is related, it looks like, to a geometric series, but it's not a geometric series because we have the n that's up here. But we do have an nth power, so that's the reason I'm thinking of the root test. So I begin, okay, for the root test, okay, we need to consider the limit of the nth root of the absolute value of the terms. Well, here the nth term, a sub n, is n over 3 to the n power. So we have the absolute value of that underneath the nth root. That's what we've got to do to decide. Now, if this is less than 1, if the limit is less than 1, then the series converges. If the limit is greater than 1, then the series diverges. And if the limit is equal to 1, we don't know. So we're going to look at that limit. Now, in this case, since n is starting at 1 and going to infinity here in the original series, the only n's we're interested in are positive n's. And so this is always going to be positive, and so that absolute value is of no consequence to us. Now, whoops, got ahead of myself here. We could think of this basically, this nth root is the nth root of the numerator, the nth root of n, divided by the nth root of the denominator, the nth root of 3 to the n power. And so all I've looked at is the nth root of 3 to the n power, of course, is just 3. The square root of 3 squared would be 3. The square root of 3 cubed would be 3. The cube root of 3 cubed, and so on. So the nth root clearly of 3 to the n power is just a 3. And so that's where this 1/3 came from, the 3 from the denominator that when I took the nth root. We still got the nth root of the numerator, or the nth root of n. Now, dealing with the nth root of n, we go back. This is something that we may have forgotten, but we've studied. The nth root of n is the same thing as n to the power 1 over n. And so we're wanting to know what the limit of n to the power 1 over n is. Now, here's the way we did that. Let me get this all out here. We did this back when talking about L'Hopital's rule. Think of n to the power 1 over n as e to the power, the natural log of n to the power 1 over n. Remember, e to the natural log of something is just the argument of that natural log. This is a fancy way to write that, and that's what we did long ago. Now, in this exponent up here, because we have a 1 over n exponent on the argument, laws of logarithms allow us to write that 1 over n as a factor in front of the logarithm. So I'm just using algebra there. And so this ends up being the limit of e to a power natural log of n over n. So that's all we've got right there. Okay. Now it's maybe a leap here for you to go from this stage to this stage, but I hope that you recall that from algebra, basically. So now if we're taking the limit of e to a power, that's the same thing as e to the limit of the power. I mean, e is constant, isn't it? So it's just the limit of that power. Well, the limit of the natural log of n over n, as n goes to infinity, is of the form infinity over infinity. It's the indeterminate form infinity over infinity, because natural log of n goes to infinity as n does, and n goes to infinity as n does. So we can apply L'Hopital's rule to this limit. And L'Hopital's rule says, oh, okay, to do that, what do? We take the limit of the derivative of the numerator divided by the derivative of the denominator. Well, the derivative natural log of n is 1 over n. The derivative of n is 1. So we're just taking the limit of 1 over n over 1, and as n goes to infinity. Of course, the limit of 1 over n as n goes to infinity is 0. So this ends up being e to the 0 power, which of course is just 1. So our original limit up here we know is equal to 1, and this is the same thing as the nth root of n, and so the limit that we get here, okay, the limit of n to the power 1 over n is 1, so we have 1/3 times 1, which of course is 1/3 and is less than 1. What did we say? If the limit of the nth root of these absolute value of the terms is less than 1, then that tells us, according to the root test, that the series converges. What we were testing is something about the terms, but now that we know that test for the terms, that limit is less than 1, we know the original series converges. Pretty easy test to apply. Let's look at another example. Okay, we're to determine the convergence or divergence of the series, sum from n equal 1 to infinity of e to the power 2n divided by n to the power n. Well, we have, we have an nth power here clearly, and we have something, of course, similar to an nth power here. So again, if I wasn't studying the root test right now, I would still consider, if I knew about the root test, I'd still consider the root test on this. Seems a natural fit. And so remember, to consider the root test, we have to look at the limit of the nth root of the absolute value of the terms of the series. So that's what we've got to consider. So we begin to do that. Well, here again, because n's are positive, each of these terms is positive, and so the absolute value is of no consequence. Again, we're taking the absolute value of positive numbers, which is just those numbers. So that's the first thing we consider. Now, I've said here that the nth root of this expression ends up just being e squared over n. Let me show you how I made that decision. Right now, we're not concerned about the limit. We're concerned about simplifying what we're taking the limit of. And so I've written it over here. Well, the limit of a fraction, excuse me, the nth root of a fraction is the nth root of the numerator or the nth root of the denominator. Now, in this numerator, it happens to be real convenient to think of e to the power 2n as e squared being raised to the n power. And clearly, the nth root of e squared to the nth power, or the nth root of something to the nth power, is just that e squared. And below, I'd already done this, the nth root of n to the power n is just n. It's just this base n. And we could actually think of this in several ways. This nth root we could think of as a power of 1 over n. And so we would have e to the power 2n raised to the power 1 over n. 2n times 1 over n is 2, so we could get that. Here we could think of this as the power 1 over n on n to the n power. And so we'd multiply the powers n and 1 over n, and n times 1 over n is just 1, so we'd have n to the power 1. Now there's multiple ways of thinking of that. But bottom line is, of course, this whole thing simplifies to e squared over n. Make sure you understand how I made that decision, because those are the things that you have to do when you're applying this test. Well, clearly, e is just a constant, and so we have a constant over n, and as n goes to infinity, of course, the denominator is getting unboundedly large. A constant number over something that's getting unboundedly large, this limit's simply 0. And 0 is, of course, less than 1, and so the first criteria is satisfied. The limit of these nth root of these absolute values is less than 1, so the the series converges according to the root test. The original series, this is what converges. This sum converges. Pretty easy to apply, as I said before. Well, I have several examples illustrating this. Just we'll go through a couple more, and just showing you different forms. Okay, here we're to determine the convergence or divergence of the series that we see here. And of course, this big power of n out here makes me think of the root test, and so that's what I'm going to apply. And just a reminder over and over, to use the root test, we calculate an nth root of absolute value of the terms. Okay. Now, here I have to be a little bit more careful about taking the absolute value away, and because I have this -3. I mean, clearly, if n is positive, this denominator is going to be positive, isn't it? It's not so clear when we have subtraction involved that the numerator would be positive, but the smallest n is 1, and so we'd have 4 minus 3 in that case, which is positive. And anytime n is bigger than 1, of course, we're going to have something here larger than 4 minus 3, which is positive. So all the terms are positive, but it is important that we recognize that we have to think about that. And so the absolute value of these terms is just the terms themselves. So this is the limit we're going to be looking at. And the nth root of something to the n power is just the radicand, what we have that power on. So now this converts to the limit of the fraction 4n squared minus 3 over 7n squared plus 6. Now, maybe we know that limit real quickly, and at this stage of our in calculus 2, we probably ought to know that this limit is actually 4 over 7, but let's go through the steps. What we end up doing, if you recall from calculus 1, is we would take the largest power of n in the denominator, which is n squared, and so we'd say either divide the numerator and denominator both by n squared or multiply both by 1 over n squared. And when we do that, of course, 1 over n squared times 4n squared just reduces to 4, minus 3 times 1 over n squared, which is this expression. And 1 over n squared times 7 times n squared, the n squareds cancel, so we're left with 7. And of course, 1 over n squared times 6 looks like this. And so now when we're taking the limit of this expression, we have 4 minus 0 when we take that, when as n goes to infinity, this term is 0 and this term is 0, isn't it? And so we end up with 4 over 7, 4 minus 0 over 7 plus 0 as we take that limit. And of course, 4 over 7 is less than 1. And since it's less than 1, we know this series converges. And what do we mean? Of course, we mean this original series converges. That is, that sum is finite. That's what we mean when we say the series converges, that the sum is actually finite. An infinite sum is finite. Well, let's look at an additional example. Does the series sum from n equal 1 to infinity of 2 to the n power over n to the power 10? Now, 2 to the n power is the real issue here. I'm thinking of nth roots because of the root test. And there's other tests that potentially I could use. This is the one I'm practicing now, and it seems reasonable because of this n power. So as we already know, to use the root test, we've got to consider the limit of the nth term, or the nth root of the absolute value of the terms. And so in this particular case, that looks like this. The limit of the nth root of the term 2 to the n over n to the power 10. And of course, those are all positive, and so the absolute value, once again, is not a big deal here. Now, the nth root of 2 to the power n is just 2. The nth root of n to the power 10, well, this is what I was discussing on the previous page. An nth root we can think of as the power as 1 over n. So we have n to the power 10 raised to the power 1 over n, and 10 times 1 over n is 10 over n. So this is what that radical simplifies to, if you will. Well, I'm going to use the same little trickery, if you will, cleverness, let's call it that I've used previously. Think of this exponent now as 1 over n times 10. So let's write this whole expression in the denominator as n to the power 1 over n, that raised to the 10th power, because that would be the power 10 over n, wouldn't it? Now, the limit of n to the power 1 over n is just 1, isn't it? See, that's what we did a couple of times ago. The limit of n to the power 1 over n is just 1. And so this whole expression, this whole limit, is going to be 2, the limit of a constant, divided by, well, this limit ends up being 1, and we have to the 10th power. So we end up having the limit as 2 over 1 to the 10th, and of course 1 to the 10th is simply 1. So 2 over 1 is 2. And since this limit is bigger than 1, our limit's 2, it's bigger than 1, that tells us the series diverges. That's a different result than we've had. So what we've learned is this series diverges, which means this infinite sum is infinite. It continues growing as we continue adding. That's not a good statement. Not that it continues growing unboundedly. It gets infinitely large. Well, that's the end of the examples for the root test. You can see it's pretty easy to use, and the root test and the root test and the ratio test, which is somewhat related to this, are two of my favorite tests for divergence and convergence. Well, good luck on your homework.